Hello, everybody. Welcome back. In the last two videos, we looked at the sampling distribution of the sample mean. In this video, we will be looking at the sampling distribution for counts and proportions. So let's recall that a parameter is a quantity that is calculated based on the entire population of measurements, and a statistic is a quantity or a measurement that is based on the measurements in a sample. So a statistic is used to make inference about the population parameter, or it is used to approximate the population parameter. So the distribution, the sampling distribution, is going to play a big role in making inferences possible. There are, of course, necessary assumptions on the relationship between the sample statistic and the population parameter. So like I said, in the last two videos, the sample statistic was the sample mean, and the population parameter was the population mean. And so the mean for any variable. In this case, we'll be looking at the parameter that we are interested in is not mean; it is going to be count and proportion. So let me start by an example to explain what proportion and count we are going to look at. So basically, we are going to look at dichotomous variables. So these are variables with exactly two outcomes. And so when you have a dichotomous variable, you have two outcomes. And since there are only two outcomes, categorically, we will label one of them as a success, and the other outcome will be labeled as failure. In short, we'll say one of the outcomes is S, the other outcome is F. So as an example, let's say that we are looking at the presidential election between Trump and Biden, and the variable of interest is the voter preference. So let's say we want to know whether so we're looking at whether voters prefer Trump or not. So the voter preference here has two outcomes here. One of them is that yes, they prefer Trump, and the other. So a voter may prefer Trump. That's one of the outcomes. A voter may not prefer Trump. That's the second outcome. So not preferring Trump, let's say, is the same as preferring Biden, but even though that may not be exactly true, but for the sake of this example, that's what I'm going to assume. So what would be the goal for looking at this variable? Well, the goal would be to find out what percentage of voters to find out the percentage of voters who prefer Trump. And percentage is the same as the proportion. So you're looking at, we want to know what proportion of voters prefer Trump. Now, so in this example, what's the parameter? Well, the parameter would be either either the count, which means the number of voters who favor Trump among all the voters, or the parameter may be the proportion of voters who favor Trump among all the voters. Now, if the population parameter is proportion of voters who favor Trump, then what is the sample statistic here? Well, the sample statistic here would be the proportion of voters who favor Trump among the sampled voters. And if we're interested in the count, then we're looking at how many voters in the sample prefer Trump. So obviously, as we noted when we looked at sample mean and population mean, we saw that sample mean varies from sample to sample. Similarly, the sample proportion varies from sample to sample. That is, if we pick a sample of voters, let's say of 300, let's say we pick a sample of 300 voters, the proportion of voters who prefer Trump in that sample is most probably going to be different if we pick another sample of 300 voters. So sample proportion will vary from sample to sample, and in order to make inferences about the population proportion from sample proportion, we need to make assumptions on the distribution of the sample proportion. So the variable here that I have, the voter preference, we can encode that in a variable, in a random variable in the following way. So let's say that x is 1 if Trump is favored. So you pick a voter and you ask, do you prefer Trump? And if he prefers Trump, then the x value is 1. Otherwise, the x value would be 0. So again, x is 1 if Trump is preferred, and we're going to call that categorically success, or S, and x would be 0. Else, that is Trump. In this case, Trump is not favored. We're going to categorically call that a failure, or F. So again, we are looking at a dichotomous variable, so it has exactly 2 values. Now, we're going to let P denote the true population proportion of voters who prefer Trump. So there is an actual proportion of voters who prefer Trump, and who prefer Trump among all the voters. So that's P. Now, P hat is the proportion of voters in a sample who prefer Trump. So P hat is the sample proportion, and P hat later on we'll see that P hat is what we want to use as an estimate for P. So in other words, we want to make inferences about P based on P hat. Now, so when we have a sample, let's say that we have a sample of size n, then the sample measurements can be represented by using variables. So let's say I have variables x1, x2, xn, and each one of them is a copy of x. And the way we're going to interpret them is that x1 is the measurement of x for the first voter in the sample. X2 is the measurement of x for the second voter in the sample, and xn is the measurement of x for the nth voter in the sample. So we have a sample of size n, and so notice that the values of x1, x2 up to xn will change when we change our sample. And now, what happens if I add all these variables? Well, notice that x1, x2, x1 is either 1 or 0, right? And it's 1 whenever Trump is preferred or favored, and it is 0 whenever he's not favored. So x2 is similarly 1 or 0 and so on. So if you think about it, then if I add these variables, I will be getting the number of voters in the sample of size n who prefer Trump. In other words, since I labeled favoring Trump as success, so this sum is giving me the number of successes in my sample. So we're going to use the y to denote the sum of the variables x1 to xn, and that's going to be the number of successes. Just to make sure that you understand why this sum is giving us the number of voters, so let's say that I only have a sample of size 3, so x1, x2, and x3. And so if I'm looking at this sum, right, let's say that x1 is 1, x2 is 1, x3 is 0. So that would mean that the first voter in the sample favors Trump, and the second voter in the sample favors Trump, and the third voter doesn't favor Trump. So if we add 1, 1, and 0, we get 2. That means 2 of the voters favors Trump. Okay, so let me give another example. So here's another example. Let's say I toss. So this is a purely, this is a classical example. Say I have a coin. Let's say that I'm tossing, and if I toss a coin, I either get a head or a tail. And since I have only 2 outcomes again, getting a head, I'm going to call that a success, and getting a tail, I'm going to call that a failure. So S or F. And if it is a fair coin, then the probability of getting a head would be 0.5. So that is one way to interpret this probability is that if I toss the coin repeatedly many times, then the proportion of tosses that will end in a success will be 50%. So in this case, again, I can use a variable x where x is 1 if I get a head from the toss, and if it is 0 otherwise. That is if I get a tail. So if I toss the coin n times, right? So in this case, what would be the population? The population would be, the value of x for all coin. So if I imagine that I toss the coin forever, and look at observe the value of x, right? And the set of all values of x from all the tosses is my population here. And if I now I'm looking at a sample of size n, that is, I'm going to toss the coin n times and observe the number of successes. So y, it is x1 plus x2 plus xn, and so each x1 is the value of x from the first coin toss, x2 is the value of x from the second coin toss, xn is the value of x from the nth coin toss. And so if I add them, then y is basically the number of heads in n tosses. And so that is y is the number of successes. And then what is the sample proportion here? Well, it is y divided by n. That is, it is the number of successes divided by the number of trials here, number of tosses n, and that's the proportion of heads in n tosses. So that's p head. And it turns out that that y has a binomial distribution with parameters n and p equal to 0.5. And I'm going to explain what this binomial distribution is in a bit. So in this example, if I take a sample of size n, that is, if I toss the coin 3 times, then notice what's going to happen in that case, y could be either, so y is the number of heads, right? So y would be either 0, 1, 2, or 3. Now when y is 0, and the probability that y is 0 is going to be 1/3, the probability that y is 1 is going to be 3/8. Sorry, the probability that y is 0 is 1/8. The probability that y is 1 is 3/8. The probability that y is 2 would be 3/8, and the probability that y is 3 is 1/8. Now, we have seen this probabilities before, so I'm not going to explain much in here. For now, I'm going to ignore the two columns that I have here, but basically, if y is 0, then what's the count of heads? Well, or the count of success? Well, 0. And in that case, the sample proportion of head would be 0. And if y is 1, then the count of successes would be 1, and the sample proportion of heads would be 1/3. So that's that. So that's another example of a dichotomous variable where we look at proportions or counts. Here's now the general setting, right? So we have a dichotomous variable, and since it has exactly two outcomes, categorically we're going to call one of them success, the other one will be called failure, and so S will denote success, F will denote failure, and X would be 1 if we get the outcome S, and X would be 0 if we get the outcome F. And so here again we take a sample of size n, and we can model the sample by using random variables x1, x2 up to xn. So again, x1 is the measurement or the value of x for the first item, or for the first case in the sample. X2 is the measurement of x for the second case in the sample, and so on. Now, if I add x1 to xn, and if I call that y, then again y would be the number of successes. That is, it is the count of the outcome s in the sample. And p hat would be the sample proportion of s. So it will be y divided by n, because y is the number of successes in the sample and n is the sample size. So y is how many successes I have in n from n cases, and the y, it turns out that the distribution of y is the binomial distribution with parameters n and p approximately, and the rule of thumb is as long as the population size is at least 20 times the sample size, the distribution of y would be approximately a binomial distribution with parameters n and p. So okay, so the question now is, what is this binomial distribution that I mentioned a couple of times? Well, the binomial distribution. So again, we'll look at the probability mass function associated with this distribution. So the distribution is this. So if y has binomial distribution with parameters n and p, now here y is a discrete random variable, so it has a probability mass function. That is, what's the probability that y is equal to k? Well, the probability that y is equal to k is given by this binomial coefficient n choose k, p to the k times 1 minus p to the n minus k. So here k is any value between 0 and n. So when you're looking at a b and p here, basically what we're looking at is that we have n trials, and from each trial we have exactly two outcomes, success or failure, and P is the probability of getting a success. So this is we're looking at a dichotomous variable with two outcomes, and the probability of success is P, and then we have n trials. So now the n trials could be exactly like tossing a coin n times. N trials could be that we are taking a sample of size n from the set of all voters, and then each one of them is asked whether or not they prefer Trump, and so that's where the n could be the trial. So each trial is basically asking a voter who they prefer. If I have an assembly line where some products are coming out of where there is some sort of product, and then if I check, let's say computer, right? So let's say laptops. So then I check each laptop for whether it has a defect or no defect, right? So then each trial is observing whether a laptop has defect or no defect, and P would be the probability of defect in that case, let's say. All right, so now I need to explain. So everybody, I'm pretty sure, understands what P to the K is, and 1 minus P to the n minus K is. It's just, this means you're multiplying P K times, and then this means you're multiplying n minus P n minus K times. So you may not be familiar with this binomial coefficient n choose K. So n choose K, this is known as the binomial coefficient, and in your calculator you might see the symbol NCR or NCK. This is how this is an alternative notation for this. And to explain what the binomial coefficient is, let me first tell you that if I have m factorial, so this symbol here means factorial. M factorial means m times m minus 1 times m minus 2 dot 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 times 2 times 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is equal to 120. 0 factorial by convention we'll call that 1. So what is what is the binomial coefficient 5 choose 2 then? Well, 5 choose 2 is 5 factorial over 2 factorial and times 5 minus 2 factorial. In other words, it's 5 factorial over 2 factorial times 3 factorial. And then we can 5 factorial is 5, 4, 3, 2, 1. 2 factorial is 2, 1. 3 factorial is 3, 2, 1. And then we simplify that, we get 10. So you can see so you need to understand what is the meaning of the factorial notation, and then the 5 choose 2 means 5 factorial over 2 factorial times 5 minus 2 factorial. Now here is generally, so here the n choose K is the binomial coefficient, and it means n factorial divided by k factorial times n minus k factorial. Now what is the meaning of this n choose K? Well, n choose K, so imagine that so we have 15 students in our class, and let's say that I want to create a committee of 3 students. So then so how many committees can I make? So if I have 15 students and I'm making a committee of 3 students, how many different committees are possible? So, well, that's exactly 15 choose 3. So n choose K is the number of ways we can pick K objects from a set of n objects, and that is the number of ways, or you can say it's the number of ways K successes occur in a sequence of n trials. So n choose K is the number of ways K successes occur in a sequence of n trials. So let me explain that a little bit by using an example. So let's say I'm tossing a coin. I'm tossing a coin 3 times, right? So n is 3. I'm tossing a coin 3 times. And so how many ways can I get 2 heads? Well, so I'm claiming that, okay, 3 choose 2, right? 3 choose 2 would be the number of ways I can get 2 heads. Well, what is 3 choose 2? Well, 3 choose 2 would be 3 factorial over 2 factorial times 1 factorial, which is going to be 3. So I'm saying there are 3 ways I can get two heads. Well, and we know that's exactly true because I can get 2 heads and then a tail. I can get a head, tail, head, or I can get a tail, head, and head. So you can see that so the 3 choose 2 is the number of ways I can get 2 heads from 3 tosses. That is, again, remember we are calling getting a head as success. So 3 choose 2 is the number of ways I can get 2 successes in 3 trials. All right, so now we can say something. So now I come here and so let's recall again that we are looking at a dichotomous variable. So it has exactly 2 values, 2 outcomes, and one of them is success, the other one is failure. And P is the population proportion, or this is the probability of getting a success, and N is the number of trials, and Y is the number of successes from a sample of size N, or you can say Y is the number of successes from N trials. Now the mean of Y turns us, if Y has binomial distribution, then, well, remember what it means to have binomial distribution. So to say that Y has binomial distribution, it means that the probability of each value of Y is given by this formula. And so the mean of Y turns out that is equal to the sample size times the population proportion, or the probability of getting a success. The variance of Y turns out to be NP 1 minus P, and the mean value of P hat turns out to be so P hat, remember, is the sample proportion. It turns out to be P, and the sigma P hat squared turns out to be P times 1 minus P over N. So in order for us to be able to use these formulas, we're going to have to assume that we have a large population. So remember the remark that I made a few minutes ago, that the population size should be, as long as it's 20 times the sample size, then we can assume that the dichotomous variable has binomial distribution, and we can apply this formulas to find the mean proportion, mean sample proportion, and the variance of the sample proportion. So again, remember, sample proportion, right? Sample proportion changes from sample to sample. So you can think of the sample proportion as the random variable, and then it does have a mean, and that mean is given by P. Similarly for the variance. So here I have 3 pictures of the binomial distribution, B and P. So when n is 10 and P is 0.5, this is the histogram for the binomial distribution. So here, we have the probability that x is 5 is given by this height here. The probability that x is 4 is about 20% or 0.2. Here are 2 others. So in the first, this one, the only thing that I changed here is P is now 0.8, and notice that the way notice the shape of the histogram here, and then when p is 0.2, that is when, so here the case is when p is bigger than 0.5. So when p is 0.5 exactly, so notice that the distribution is symmetric, right? And in this case the distribution is not symmetric, and also in this case the distribution is not symmetric. So this is the case when p is 0.2. Okay, so I think I am going to stop the video here, and in the next video I will carry out some examples.